Hi, I'm Devi Priyanka Gantla. I want to sincerely thank Professor Sangsu for this opportunity and his guidance throughout the development of this project. Today, I'll be presenting a project titled Video Based Large Language Model for Enhanced Temporal Understanding, a research initiative that conceptualized, implemented, and evaluated independently. First, let me take you to the outline of this project where it involves the motivation I got to do this project statement that related works that I've referred, the literature review, the approach for this project, the code implementation, and training pipelines through which I got the accurate results and the performance analysis. I'm going to give you a live demonstration of the code inputs and outputs in my video for clear understanding and also the future work and conclusion of this project. First, the motivation behind this work stems from growing dominance of video content in our digital ecosystems. Videos are no longer just for entertainment. They are communication tools, educational platforms, documentation sources, and surveillance data. However, understanding the semantic meaning of videos is complex because it involves interpreting both visual and auditory modalities and their evaluation over time. This project aims to build an AI system that can intelligently interpret and reason about such temporal information in videos. Coming to the literature review, to address this, I explored recent advancement in multimodal large language models, particularly video LLAMA and video chat, and then designed a customized architecture that builds upon their strengths while introducing original innovations. The three core innovations of the system are adaptive frame sampling. The method allows the model to dynamically adjust the frame sampling rate based on their motion density in their video. For fast moving scenes, more frames are sampled, while static scenes were handled with fewer frames, which reduces computational overhead without compromising contextual understanding. Coming to the second, the Modal Fusion Bridge. This is the novel mechanism I implemented that allows the audio and video streams to interact deeply. It uses bidirectional attention and a dynamic fusion strategy that learns to prioritize either audio or video based on the importance of given in the given context. Enhanced temporal position embeddings. Unlike traditional embeddings, this approach explicitly encodes the time gaps between frames, which helps the model better grasp the sequencing of the actions, particularly when events unfold gradually or over long spans. Coming to the problem statement, here's a training structure I've used, where in the video dataset, I have a lot of videos where I took one video as a consideration for frames extraction. Here you can see two different frames extraction. One is with 6 frames and the other with like 10 to 12 frames. But I consider 10 to 12 frames to go to the next procedure because 6 frames, like when you want to know when did the person threw a ball in this video, because this is a fast running video, you cannot uh, know when exactly he threw a ball with just 6 frames. So you need 12 fps, that is like frames per second. So that's why I consider 12 fps for the next step to go ahead. So this goes to the image encoder. Image encoder acts as a transformer encoder. First, let me tell you what exactly an encoder job is. Encoder is something that is used for classification, and decoder you might have heard a lot about these days, that is used for ChatGPT and Grok, where decoder is used for generative purposes like text, image to text, audio to text. So this is like completely interactive way. So this is combined, this is a model that is combined. Like, this is like basically used for ChatGPT too. So that is for the encoder and the decoder, both are combined in this, that is called temporal architecture, where I can show you one image. Transformer architecture, where this is called encoder and this is called decoder. These two combine to work and give output probabilities. That is called transformer encoder. Okay, from the transformer encoder, from you will be like, so this transformer encoder, the image encoder actually acts as a transformer encoder and gives the output. So firstly, how does an image actually go and give us good classification? So to go this, I'll take you through in depth. So here you can see a lady playing tennis With this picture, this goes to CNN using the video using an image algorithm, where the CNN is an algorithm that is used to split the image into different types of patches, and that is used for visual encoders too. So first let me explain you what exactly the patches does. Here you can see an image of a dog. Those images are like splitted into patches. These patches are, every patch, these 9 patches have different numbers associated according to the picture. These numbers are actually given according to embedding vectors. Embedding vectors is something like um, that is used for that is used to know if you here you can see a puppy, but a puppy is basically related to dog, you know that, but how do a machine know that? So for this we use word to vec. Let me explain you. word to vec Word to vec is something like this. On a three-dimensional spatial representation, here puppy has a patch number called 312, and a dog patch number has a number called 350. Those, the differences between both of them is like 2. So it gets easily uh, directed to the less difference. So puppy is directed to dog. That's how this word to vec is done. So where the patch of the image, so the image patch is described, this is how it is described to a word, and from the picture you'll be getting the words too. So this happens with audio to word, image to word, word to word, and all. And from these patches, these are again classified into different classes, and all together these are maintaining a placement, a good placement with no disturbances, and these placements are then sent to the transformer encoder. Now this transformer encoder is now sent to the temporal and spatial description. What is exactly temporal and spatial description? Temporal and spatial description is like, temporal is to know when did this happen, how did this happen, and all. Spatial is what exactly happening around the main subject. For example, here I'm a person giving you this presentation. I am temporal, and what is exactly happening backside of me is called spatial. Say for example, I have a gray door locked, and I'm speaking here. So that is considered under spatial description, and me is considered as temporal description. So combined of these two will be trained, and that is given to a training LLM model. This data will be given to the training LLM model. The same happens with the audio extraction from the video, where the audio is extracted, and that speech is sent to the text model, and that to the audio context, and this audio context and then sent to the train LLM model. Now all of this will be getting trained, and this will be giving the best LLM model is saved with least errors happening. Okay, now the least error and the best model is now sent to a chatbot. So here you can see the input video is sent to a chatbot, where this chatbot is used as an as an interactive tool, where you send a video and you ask, when did Rodriguez score the 3-pointer? So from the best saved LLM model, this gets trained and gives us the output when exactly that had happened. Rodriguez scored the 3-pointer at 2.45 remaining in the third quarter, reducing team's A defect, and blah blah blah. That is all the output that you get from the output video frame. So it's actually giving you the correct time. Like the question that you've asked for is, when did Rodriguez score the 3-pointer? And the third quarter, reducing teams A deflect from 8 to 5 points. And 2.45 is a 3-pointer that had happened. And Smith provided the assist. So it's complete analyze is given through this text, and also the video frame when all this had happened is also been given. This is how my model works. Coming to the implementation, let me take you through the code once. Coming to the implementation, let me take you through the code. Yeah, this project uses the Kinetics-400 dataset, a large-scale video dataset, where each dataset used shows a person performing an action. So coming to the code, the Kinetics-400 class has a multi-class classification. For example, this has cooking sausages, wrestling, basketball, all of these. So the primary evaluation is accuracy, that is by correct prediction by total predictions. A fine-tuned model is hosted in the Hugging Face under the model section for classification. Here there are two models, that is 50 epochs and 30 epochs. For to coming to epochs, this has two major things. That is, one epoch is equal to batch of 10 and sequence length of 32 frames. And this goes as one iteration because all the data cannot be read at a time. So it does all this in an intervals with small size of data. So for example, if you go to a fish market and a fisherman tells you about 10 type of fishes all at a time, and you cannot recall everything, you cannot process everything, so you will have to learn each and everything in a step by step in a simple data set to train your data, I mean to train your brain that to differentiate what fish is and what is it. So that's how here also happens. So all at a time with all 100 videos, you cannot train a data, you cannot train the model, you can only train the data with simple, I mean with simple batch size frames. And since now I do not have higher GPUs, I haven't uploaded this into spaces to host this model, so I've imported this 50 epochs as this is the best model. We've fine-tuned model called Quen 2.5 for action classification, and after fine-tuning the I've saved this into the collab and Kaggle to run. Let me run this and show it to you. First, let me reconnect. Okay, now this is connected where with one user I can get 15 GB of GPU. So that's why 15 GB of GPU for this cannot be uh, satisfied. So that's why I made it into two different notebooks, that is one into Collab notebook and the other into Kaggle notebook. So this video first, I mean this collab will be first doing the action classification. Let me tell you. Let me run the video. Sorry. Let me run the code. With the code running, yeah, this is done. And coming to the next, let me run this. Okay. This is just a video inference. And coming to this, yes, video and audio inference. This is a fine-tuned model. Let me run this. And during this run, you can see different fluctuations in the system RAM, GPU RAM, and disk. You can see here when this exactly runs, there will be graph growing up, how much GB that is being used. And moreover, to explain about this uh, thing, this is where I've connected the 50 epochs that I've used in the Hugging Face. And here I've used the Whisper processor, where this is used for is used for best classification. That's like fine tuning. Like this transcription can be done for the image, for the text also, for the audio, for the text. So this Whisper processor is mostly used, and this is still running. This is the Quen that I've attached here, the Whisper processor. I think I ultimately, simultaneously, I can also run this. Let me also connect. Okay, here you can see a GPU that is being used as an accelerator, and I'm also running this simultaneously. I think I should still, it's still working. See, here you can see the GPU occupying the GB. Yeah, I think it's time for the output. Yes. So here you can see, here this is the interface that I got. Let me just, here, okay. Here I got, okay, I'll have to close this resources. Yes. Okay. This video action classification is being done with the help of Quen 2.5. So here I got an interface to upload my video. I'm going to click this. This is the videos that I have. Let me put arm wrestling. And this arm wrestling video actually transcribes the audio, the model response, and the prediction action class. You can see. Now I'm submitting. See how I got the audio transcription says, "Oh, it's over, it's over." That's what those two people are saying. The model response says the action in the video is an arm wrestling match between two individuals, and the production class says this is wrestling. Let me try with an other example, another video. Let me clear this. Let me try with archery. Okay, let me play the video if I can, or no, I don't know. Yeah, here you can see a girl doing this archery, throwing the arrows. Now let me submit. This is processing. Yes, this gives the main action in this video is archery. Okay, and coming to the kegel, this is done. Let me run the other cell. This this collab interface is used for action classification. What exact to just know the classification, what to I, the, the thing that I've already told you, it's like not just through go through the entire video. It's just let you know, okay, this is like archery. Okay, fine. That's how it classifies us into a simple understanding of the video. And this is done. Let me run this. And here are the sessions that we have. The GPU, the CPU. The CPU is already done, so I think it's going to the GPU percentage usage now. I think we should be getting the chat, but still running. Yeah. It should work now. Okay, in meanwhile, let me tell you about this. The learning rate. So this is also main thing. So the learning rate that I've used here is like 5 to the 5 exponentials thing. So the learning rate should be always in a very good learning rate. Like it should not be high, it should not be low. Like I've already told you, to grasp everything into your brain, you cannot do all at a time. So you should have to do into an intervals phase. So that's why when you train a data, when you train a model, or when you using a large data sets and all, if you want to make like learning rate should not be high, should not be low, it should be in like very balanced way. So I think we should, yeah. So yeah, the thing is like the learning rate should always be minimal. It should not go high or it should not go low. I think the chatbot is almost done. It's still loading. I think we can see the GPU. Yeah, 4.1 of GB is being used. Yeah, we got it. So this is the interface to chat. This is completely a chatbot thing. So I'll upload the video of a ballet dancing. Let me play the video for you. So the trainer has adjusted the head, and these are the girls are dancing. That is what we have done. So let me ask, what's happening in the video? I've sent the question. It should give me an output now. You can see the GPU percentage that is being used. The max that we have is 15 GB. Yeah, we got it. Okay, that's what I have asked. What's happening in the video? The video shows a group of young women in the dance studio preparing for the performance. They are dressed. They're practicing helping with the hair, adjusting their positions, focused and determined. They are working hard to perfect their performance. So this is a lively and interactive chatbot that I've built after uploading the video. Like this is how I've done. This is used for the classification of the video, and this is used for chatting, like the interactive way, like a chatbot that you can ask whatever questions that you want, even more. That is my code and output. Coming to the presentation. Yeah, like I've already told you, that's the core components that I've used. the whisper processor, the video processing, and the model architecture. Coming to the next. And the chatbot that is being the chatbot that is being used here is done based on the Gradio interface. Yeah, and using this Gradio interface, I built a normal video chatbot. This is being used. So, coming to the accuracy. So for training and evaluation, I used the Kinetics-400 dataset. Interestingly, the model was trained only on 5% of the dataset, but achieved an impressive 92.6 accuracy. This not only demonstrates the efficiency of the architecture, but also indicates the robustness of the introduced components. Comparatively, this performance exceeds that of some of the art models like Video MAE, V2, which typically requires larger datasets and longer training times. The applications, these are mostly used for the education, for game purpose, for health, and for even more. And to evaluate the model real world applicability, I built a demo using Gradio. This interface allows users to upload or stream video content, and the model performs classification, even engages in a dialogue explaining its interpretation. This makes the system not only functional but also interactive, which is essential for use cases in education, healthcare, and surveillance, like how I've told you before. Despite the strengths, the system isn't without a limitation. I analyzed some failure cases and noticed that model struggles with actions which are visually or audibly, such as opening and closing a bottle. The subtle temporal difference in these activities are hard to capture, which points to the need for finer semantic modeling or even integrating tactile cues in future work. In contrast, activities like playing basketball or riding a bike were actually classified thanks to distinct motion and sound patterns. Throughout this project, I managed every step from initial research, architecture design, coding, fine-tuning the model, conducting evaluations to finally developing the user interface. It has been a deeply enriching experience. I became more proficient in using Hugging Face transformers, PyTorch, Gradio, and working with large-scale video datasets. It taught me how to optimize models for limited resource settings, which is crucial for practical deployment. Those are the contributions of this project. And coming to the future work, this needs explore additional data sets, full kinetics 700, ActivityNet, Epic Kitchens. This might just go into the scale model to larger sizes, for the integration to additional mobilities, and develop more efficient attention mechanisms and benchmarks of architecture and temporal reasoning. In conclusion, this project showcased that even with limited and data and compute, intelligent choices and innovative mechanisms can lead to high performing models. I look forward to continuing this line of work, expanding the data set, refining model components, and exploring applications like video summarizations, emotion detection, and AI companions that can understand both what is happening and when. Thank you once again for this opportunity. And sorry, before that, these are the references that I've used all through my project. And yeah, thank you once again for this opportunity, and I welcome any feedback or suggestions you may have.